U.S. Department of Transportation logo, Federal Highway Administration.
Welcome to FHWA's training video for the Excel-based Bridge Improvement Program Benefit Cost Analysis tool, hereafter BIP BCA tool. This presentation provides information for how to use the BIP BCA tool, including the goal and purpose of the tool, what you need to get started, and walks through a full example of a benefit cost analysis for a bridge investment project. The information provided in this presentation can also be found in the BIP BCA tool manual, which is available at the FHWA Bridge Investment Program website. The goals of this video are that you will be able to use the BIP BCA tool to obtain data from the National Bridge Inventory and the National Bridge Investment Analysis System. This data includes forecasted bridge load posting and closure dates, annual average daily traffic counts and growth forecasts, bridge detour length, and other values relevant to the BCA. You will also gain an understanding of how to complete a BCA that aligns with the US DOT Benefit Cost Analysis guidance using the BIP BCA tool. And finally, you'll be able to use the BIP BCA tool to complete a basic BCA spreadsheet suitable for accompaniment to the BCA memo of your BIP application. The BIP BCA tool was built for the Bridge Investment Program, a discretionary grant program which is specified in the Infrastructure Investment and Jobs Act, also known as the Bipartisan Infrastructure Law. Section 11118 F1B of the law requires that the BIP program provides applicants with a tool to summarize project needs and benefits, and 2, enables applicants to use data from the National Bridge Inventory. The tool was also designed to allow applicants to complete an independent BCA for each bridge when projects are bundled, and it provides access to the unbiased forecasts of condition rating, load posting, and closure. The BIP program encourages applicants to use the tool as it was developed to reduce the burden on applicants to complete their BCAs. The tool provides the unbiased forecasts of condition rating, load posting, and closure dates, which the applicant would not have access to otherwise. The tool can be used to acquire the unbiased forecast of condition rating without being used to complete the BCA. While FHWA encourages the use of the tool, it is not required for the BIP applications. The tool will be used by US DOT reviewers to quantify the benefits and costs of the proposed investment as defined in Section 11118 F1B of Bill, and determine the extent to which the benefits are more likely than not to outweigh the total project costs. The tool can be used for other transportation BCA applications when appropriate. The default values in the tool come from the US DOT BCA Guidance January 2023 update, the National Bridge Inventory, the National Bridge Investment Analysis System, EPA's Motor Vehicle Emissions Simulator. If an applicant changes the default values, then the applicant BCA memo needs to provide the methodology and source for the change. The tool can be downloaded from the Bridge Investment Program website at www.fhwa.dot.gov/bridge/BIP. The tool is a macro-enabled Excel workbook, so you will need to turn on macros to use the tool. Before starting your analysis, you will need an understanding of the project type and the general impacts of bridges in your project, information to identify each bridge in the MBI, including state, county, structure number, alternative values for any MBI input for each bridge, such as AADT or detour length, if you don't want to use the MBI data in this tool, the costs of the project, including both capital costs as well as operations and maintenance costs for the build and no-build scenarios, and finally, information specific to the benefits you're claiming, such as annual average crashes, the annual probability and consequences of weather, seismic, or other extreme events, or pedestrian and cyclist ADT. When opening your own copy of the file, the only two tabs that will be visible are the Overview and the Select State MBI Data tab. The Overview tab covers the basic background and navigation of the tool, which is also covered in this video and in the manual. The first step in using the tool is to select the state data that you will use from the National Bridge Inventory database. The tool includes the BCA relevant data for all the bridges from the latest NBI dataset, which means that the tool or file is larger than necessary for most users. Use the drop-down in Table 1 of the Select State NBI Data tab to select up to 3 states. This step will reduce the file size of the tool, helping it run more smoothly and make it easier to email or share with others. For this example, we select My State from the drop-down in Table 1 and click the Select State NBI Data button. Alternatively, to run the macro, we can click Ctrl plus Shift plus I. An option menu will ask if you want to confirm, yes or no, and then the macro will run. This action may take a few minutes. It is critical that you do not interrupt the process. The tool has now unhidden the Example Bridge tab, the Results tab, the NBI Data tab, and the Defaults tab. The Example Bridge tab provides an example of how to use the tool to calculate a BCA and is the starting point for your analysis. Each bridge in your project will need a separate bridge tab, as all the costs and benefits are calculated for a bridge on a single bridge tab. New bridge tabs can be added using the Add Bridge button on the Example Bridge tab or by clicking Ctrl plus Shift plus B at any time. All input fields and drop-downs are organized by tables. The inputs provided in tables 1 through 56 are used to calculate the annual benefits and costs in Table 57, which we will review in a moment. Any cells that are green, bold, and underlined are required to be filled in by the user, and without entering a value will lead to errors. Notes providing additional information are also provided, which appear in yellow boxes on their own row and are designated by the word Note. These provide helpful information for how to use the tool and tips for best practices on critical functionality. For the most important critical cells, the word required is the default value to alert the user. Any cells that are blue, italic, and underlined are optional, and users can provide that information if necessary or desired. Any cell that is gray or has no text format represents NBI or other US DOT BCA guidance formula. Gray or no text without formatting should not be changed. Changing those cells could lead to errors in the workbook. The Results tab provides the results of any bridge project included in the analysis. Table 1 captures all of the results of the bridge analyses included that the user has generated, and it includes all of the benefit and cost categories as rows and the bridges as columns. You can use the Include or Not Include drop-down to select whether to include a bridge project in the overall results. In Table 1, we select Not Include for the example project, and now the total value in the table is 0. We can reset this by clicking Include in the drop-down again, so that the example bridge is now included in the total column. In Table 2, you can enter your unquantified benefits, which includes bundling cost savings, alternative design cost savings, and other benefits. In Table 3, you can select whether to include the different benefit categories by using the drop-down. In this example, we will select Not Include for safety. And now in Table 1, the safety value in the total column is empty. And we can reverse that again by selecting Include for the safety row in Table 3. The Defaults tab provides all the default values used in the tool, including those from the US DOT BCA guidance and the emissions estimates from the EPA MOVES model. The NBI Data tab will have the bridges from the states that you selected on the Select Bridge tab, as well as the M-bias forecast for the bridge condition ratings. In this example, the only bridge is our example bridge project. Now we are going to create a new bridge tab to replicate the analysis on the example bridge tab. On the example bridge tab, use the Add New Bridge button, or alternatively enter Ctrl-Shift-B to create a new bridge. A pop-up menu requires us to name the new bridge tab, which we will call New Bridge. In addition to creating a new bridge tab called New Bridge, the macro adds our bridge to the Results tab, Table 1. There are no benefits or costs in this column for our new bridge yet because we haven't entered any information. On the freshly created New Bridge tab, there are 3 additional buttons that you can use that are not on the Example Bridge tab. These allow you to create a sensitivity analysis, to delete the Bridge tab, and to change the Bridge tab name. To add a sensitivity analysis, click the Add Sensitivity Analysis for the current bridge button, or press Ctrl plus Shift plus S, and this will create a new bridge tab called New Bridge _SNS. It takes the bridge name that you've entered and adds _SNS. The tool copies over all of the values that you've entered on your previous bridge tab, and then you'll be able to adjust any inputs that you want to test the sensitivity of. For instance, you could change the annual average daily traffic values. In addition to adding a new tab, when you add a sensitivity analysis, it adds the sensitivity analysis column to Table 1 on the Results tab, which you can use to include or not include in the overall analysis. In addition to the Add Sensitivity Analysis button, you can click the Delete This Bridge button or press Ctrl plus Shift plus D, which deletes the current bridge. In this case, we will delete the sensitivity analysis that we just created by clicking the Delete This Bridge button. Do not delete the bridge tabs using any other method than the Delete This Bridge button, or you will break the results table on the Results tab. You need to only use the Delete This Bridge button. A pop-up asks to confirm the deletion, and we confirm by selecting Yes. So now the sensitivity analysis that we created has been removed from the tabs, and it's also been removed from Table 1 BCA Results on the Results tab. The final button is the Change Bridge Name button, or press Ctrl plus Shift plus N, which changes the bridge name of the active bridge sheet. Do not change the bridge name using any other method, or this will break the reference to the Results table on the Results tab. For this example, we will change this bridge to New Bridge 2 and press OK. And now the active tab has changed names to New Bridge 2. And in the Results tab, the column that was the new bridge is now New Bridge 2. Now we will begin to enter our bridge information to recreate the example bridge analysis. The example bridge uses a fictitious bridge created to demonstrate the functionality of the tool, so the MBI data we use in the analysis is fictitious as well. On New Bridge 2 tab in Table 1, we're going to use the drop-downs to select the bridge's state, county, and structure number. For the example, we select My State for the state using the drop-down, we select My County for the county using the drop-down, and for the structure number, we're also going to use the drop-down to select 001. Alternatively, we could have entered those values by typing them. In Table 2, we enter the project timeline information. In this example, we're going to enter 2023 for the current year, 2024 for the first year of construction costs, 2027 for the last year of construction costs, and the project opens in 2028. And the year of benefits for the analysis is 30 years because this is the reconstruction of a bridge. In Table 3, you will enter the vehicle AADT. In this example, in the no-build scenario, we have passenger AADT of 6,838, truck AADT of 760, and bus AADT of 300 in the year that the project opens, 2028. These values grow to 14,245, 1,626, and 390, respectively, in the final year, 2057. For the build scenario, we enter the same AADT for the initial and final years, as the project is not expected to lead to induced demand. The tool can handle induced demand, but users should only include future additional growth in the build scenario if there's an aspect of the project that will induce additional vehicle travel. Users should note that the AADT from the MBI has been provided in the table for reference. The AADT in the MBI represents all vehicles, so in this example, the bus AADT we entered has been taken as a portion of the MBI passenger vehicles. The AADT values entered in Table 3 will be calculated for each year of the analysis in Table 54 below, which we'll review in a moment. Because we've deviated from the MBI values for passenger ADT and bus ADT by entering our own values, we will provide an explanation for that data in the explanation column of Table 3. Anytime you enter values that deviate from the MBI data, you will be prompted to provide an explanation in the last column of the table as the cell is activated in green, bold, and underlined format. Table 4 provides the MBI calculated annual growth rate. The user should not adjust Table 4. In Table 5, we enter the detour road type information. We use the drop-down to select one of the functional classes for the detour road type. In this example, we're going to use the rural principal arterial interstate. In Table 6, we enter the detour and bridge length information. For the net detour length for this project, we're going to use 2.5 miles as indicated by the MBI value. For the detour average speed, we're going to use 60 miles per hour, and this is based on observed speeds, so we provide that explanation in the explanation column. For the net detour length for cycling and pedestrians, we're going to use 0.5 miles because there is a pedestrian bridge nearby, and for the bridge length, we're going to use the MBI value of 0.16 miles. Table 7 is a reference table that provides the reference for the MBI data so that the Bridge tab can pull in all the MBI information. The user should not interact with this as it's critical for various functions in the tool. In Table 8, we enter the travel assumptions. For the bridge average speed, we enter the FHWA value of 60 miles per hour. For the average car occupancy, we enter 1.67 from US DOT guidance. We enter 0 for the share of long-distance personal travel, $23.80 for the long-distance personal travel monetary value, 11.8% for the share of business travel, $31.90 for the value of business travel, $17 for the value of travel for personal travel. The value of travel time, all purposes, is calculated based on our entries above. The value for walking, cycling, waiting, standing, and transfer time is $34 per the US DOT PCA guidance. The value for truck drivers is $32.40. For bus drivers, it's $35. For the average bus occupancy, we enter 10, which comes from our My County MPO data. The next section is the capital cost and residual value section. Use Table 9 to select whether the input cost values are year of expenditure dollars or whether they are adjusted for inflation, i.e. real dollars. You can also select the inflation rate for the capital cost if one applies. For this example, we enter no as the capital costs are in real dollars and therefore no inflation rate is needed. In Table 10, we enter the costs that have already been incurred by entering the year and cost value. The tool will automatically adjust for inflation if necessary and apply discounting. In this example, we already have incurred cost of $100,000 for both 2022 and 2023. In Table 11, we enter the capital costs incurred for each year of the construction period. In this example, we have costs of $5 million in both 2024 and 2025 and $10 million in 2026 and 2027. Table 12 contains the capital cost summary, including the total capital costs, the total real capital costs, and the total discounted capital costs. In Table 13, we enter the share of capital cost and the asset life for that share of cost. In this example, all the capital costs are spent on one investment, which has a lifespan of 40 years. As our period of analysis is 30 years, this will generate a residual value, and we provide an explanation of the residual value in the explanation and source column. The next section is for operating and maintenance costs. Table 14 allows the user to select which method of operating and maintenance cost to use and to enter the year of maintenance cost dollars. In this example, we will be using the manual entry and the year of cost dollars is 2021. The frequency calculation method uses inputs from tables 15 and 16a through d to enter the annual maintenance costs. For table 15, you would enter the annual O&M costs for the build and no build scenario and the growth rate for those costs over the period. The tool will calculate the difference. For tables 16A through D, enter the initial year of the cost occurs, the last year the cost occurs, how many years the cost occurs every X year, which can be 1 through 30, as well as the O&M costs in the no build and build scenarios. In our example, however, we will use the other approach, the manual O&M input approach. In Table 17, we enter the manual O&M costs. In this example, we have $10,000 of costs every 4 years, starting in 2023 and ending in 2055. In the build scenario, there is $1,000 of costs every 4 years, starting in 2023 and ending in 2055. The bridge is anticipated to be closed in the no-build scenario by 2050, so the O&M costs stop recurring in 2050. The build scenario will continue to have recurring O&M costs of $1,000 every 4 years through 2055. The next section is for construction disbenefits. In Table 18, select Yes in the drop-down if the construction of your project will lead to disbenefits. Whether the project has construction disbenefits or not, you will need to explain why and how those impacts were determined in the explanation cell in Table 18 as well. We select Yes in Table 18 and we provide our explanation that construction will close one lane of traffic on the bridge, alternating directions at 75 days. Pedestrians and cyclists will continue to be able to use the roadway during construction with no expected delay, and the crash risk is expected to increase marginally given the construction zone. Table 19 and Table 20 have been activated. In Table 19, you can estimate your travel time and safety disbenefits for each year of construction. The table will automatically calculate the total disbenefits and discount those values appropriately. For travel time disbenefits, enter the AEDT affected by each mode and year, the travel time impact for each mode, as well as the days of impact annually. These values will be entered in the pre-benefits row of the final table, Table 57. For safety disbenefits, enter the percent increase in crashes due to the work zone. Safety crash cost increases will be calculated based on the baseline crash rate entered into Table 36, which we will review in a moment. In this example, we are going to enter 6,200 for the passenger AEDT in 2024, which will escalate by 200 to 6,800 in 2027. We'll enter 680 for truck AEDT, which escalates by 20 to 740 in 2027. And we'll enter 260 bus AEDT, which will escalate by 10 up to 290 in 2027. The vehicle delay is 1 minute per vehicle trip, and the number of delays of impact annually is 150. For safety benefits, we enter 5% increase in crashes due to the work zone, and because we haven't entered information into Table 36, the total safety discounted benefits do not yet calculate. In Table 20, enter any additional disbenefits besides travel time and safety impacts. In Table 20, we enter an additional impact of the cost of police detail, which is a one-time cost of $300,000, which is required for the construction. The next section is for entering the bridge condition and closure information. Select Yes in the drop-down in Table 21 if the project will improve or preserve the bridge's condition in a way that reduces the risk of closure and/or load posting. In this example, our project improves the bridge's condition, so we'll select Yes. In Table 22, Bridge Details, it provides the relevant information from the MBI used to estimate the potential of closure based on the M-bias forecast of bridge condition. Table 23 provides the year of the M-bias forecast of overall condition rating of 3 and 2 and the superstructure condition rating of 4 and 3. In Table 24, Anticipated Load Postings, you will enter the anticipated year and impact of load posting as a percent of bus and truck traffic detoured. There are 3 levels of load posting. In this example, based on an engineering study, it is anticipated that in 2035, the bridge will be load posted, allowing only 50% of existing truck and bus traffic, and then in 2042, load posting will not allow any bus or truck traffic. In Table 25, we enter the anticipated closure information, including the year the bridge is expected to be closed in the no-build scenario and the percent of all traffic that will be reduced. In this example, the bridge is expected to be closed in 2050 based on an engineering study, and this will affect all modes. In tables 26A through 26D, you can enter in intermittent closures by entering the initial year, the last year, how often the closure occurs over the period, the number of days of closure, and the percent reduction in all traffic. The next section is for entering whether the project includes resilience to weather, seismic, or other extreme events. Select Yes in Table 27 if the project will improve the bridge's resiliency to weather, seismic, or other extreme events by reducing damage and/or closures or other service interruptions. In this example, we will select Yes. In Table 28, select Yes if you will use the probability consequence analysis approach to estimate those impacts. The consequence probability approach requires defining a potential weather, seismic, or extreme event, the annual probability of that event, and the consequences of that event. This resiliency section is for a maximum of 3 independent events. Events with multiple levels of consequences or dependent events require more complex modeling. 3 suggested levels of consequence for each event are included to better reflect the range of consequence events that an asset may face. In Table 29, we enter the annual probability of event occurrence for the 3 levels of events. This table includes 3 independent events with 3 different consequence levels. 1. The probability of an event occurrence that causes capacity reduction only, that's entered in Table 30, i.e. not capacity reduction associated with structural damage. 2. The probability of an event occurrence with lesser structural damage consequence, Table 31, and the probability of an event occurrence with a large structural damage consequence, Table 32. The probability may change during the benefit period due to climate change or degradation of the remediation or other reasons, which can be captured under probabilities for project open and final year. You don't need to use all 3 levels of events, but they're provided in case you want to. For the volume capacity reduction only event, we use 1%. For the lesser structural damage event, we will use 0.1%, and for the larger structural damage event, we will use 0.01%. In Table 30, the volume capacity reduction impacts. In the no-build scenario, the bridge is expected to have 25% reduction in capacity for all modes for 2 days, whereas in the build scenario, it is expected to have 25% capacity reduction for only 1 day. In addition, there's $20,000 worth of repair costs in the no-build scenario and only $10,000 of repair costs in the build scenario. In Table 31, the lesser structural damage, the bridge in the no-build scenario is expected to have 10 days of closure with 50% reduction for each mode and $200,000 of repair damage, whereas the build scenario is expected to have 5 days of closure for 50% reduction for all modes with only $50,000 of maintenance costs. In Table 32, the larger structural damage, in the no-build scenario, there is expected to be 25 days of closure with 100% capacity reduction for all modes, $2 million in maintenance and repair costs, 1 fatality, and 10 injuries in year 1. In the build scenario, the days of closure is expected to be 5 days. The passenger, truck, bus, and bike reduction in AADT is expected to be 100%. The repair costs are $100,000 and the fatalities are 0 and the injuries are 0. If you are not using the probability consequence approach, select Yes in Table 33 and this will allow you to enter in your explanation of the resilience benefits in Table 34. The next section is for the safety baseline benefits, detour safety benefits, and safety countermeasure benefits. Table 35 allows you to select whether you will enter the CABCO or general crash costs. These 2 approaches are outlined in the US DOT BCA guidance, and you should use the crash cost category that is appropriate for your crash data. If your crash data are defined as CABCO crashes, use the CABCO costs, otherwise use the general approach. When we select the general costs, the tables 36, 39, and 40 will make the general costs active. However, in this example, we are using the CABCO costs. In Table 36, enter the historical crash data, including the years of data and the number of crashes by type. In our example, we have 10 years worth of data for each crash type, and the number of crashes per crash type are 20 for property damage only, 5 for no injury, 2 for possible injury, 1 for non-incapacitating injury, 1 for incapacitating injury, 0 for killed, and 1 for injury severity unknown. And because we have provided information, we need to provide an explanation of our source for this. And so we are entering the data that come from 2013 to 2022 provided by our My County law enforcement, and our details are in the BCA narrative. In Table 37, we select whether the project improves safety on the bridge via crash modification factor improvement, and in this case it does. In Table 38, we enter the time frame for these benefits. We enter 2028 as our initial year of these benefits and 2057 as our final year. In Table 39, we enter the safety countermeasure crash costs avoided. In this case, we are deploying a safety intervention that will have a CMF of 0.74, or a 26% reduction in crashes for all severities. The intervention is to introduce a positive offset left turn lane for the bridge approach, which is in the CMF clearinghouse ID 276. The table will automatically calculate the average annual crash costs avoided due to the intervention. We enter 0.74 into the CMF column for each of the crashes, and we will enter our background information in the CMF reference number column and the explanation and source column. In Table 40, we enter the crash cost per million for the detour route. The table will automatically calculate the crash cost per mile on the detour route. This is the additional safety risk incurred by taking a more circuitous route, and it's used in the safety and resilience calculations in the final table, Table 57. Be sure to provide an explanation of where the data were collected from for this table. In Table 40, we enter the crash rates from 2013 to 2022 from our law enforcement. For the property damage only crashes, we have 20 per 1 million VMT. For no injury, we have 4. For possible injury, we have 2. For non-incapacitating, we have 1. And for incapacitating, we have 0.01. For killed, we have 0.001. For injury unknown, we have 0.5. And we provide our explanation for those crashes in the explanation column. In the next section, we enter the travel time and mobility-related benefits. In Table 41, we select whether the project will improve travel time or mobility on the bridge, which is separate from reducing the bridge closures or load posting. In this case, we will select yes, and now Table 42 and 43 will be activated. We'll start with Table 43, the optional travel time savings calculator. In Table 43, we enter the speed in the no-build and build scenarios for the initial year and final year, as well as the distance traveled on the bridge, and that calculates our minutes saved per vehicle. In the no-build scenario, we enter 60 miles an hour in both the initial and final year. In the build scenario, we enter 70 miles an hour in the initial and final year, demonstrating the improvement at 10 miles an hour on average for the traveling over the bridge. And then the distance traveled on the bridge is 0.25 miles, which is the 0.16 miles distance of the bridge plus the approaches. Table 43 calculates our minutes saved per vehicle, and it's 0.04 minutes saved per vehicle. We enter 0.04 minutes saved into Table 42 by entering in the first year that these benefits will accrue. Starting in 2028, the final year, which goes all the way through 2057, we enter the minutes saved per vehicle, 0.04, in both periods, and that will calculate our mobility benefits. In the next section, we enter the mobility-related emissions and other environmental benefits. In Table 44, we select whether the project has benefits related to improved wildlife connectivity, reduced noise, or improved water runoff. In this case, we select yes. In Table 45, we enter the values for those benefits. In this case, we only have a benefit for the water runoff of $100,000 annually with a growth rate of 1%. The initial year that those benefits start accruing is 2028. The final year of those benefits is 2057. And we provide an explanation of that benefit, which is that the additional treatments on the bridge will allow the water runoff to flow less disruptively. And our full description of those benefits is in the BCA narrative. In the next section, we enter the pedestrian and bicyclist benefits. Select yes in Table 46 that the project will improve pedestrian and bicyclist facilities, or if the project will avoid detours for pedestrians and bicyclists. In Table 47, we enter the AADT for pedestrians and bicyclists in the build and no-build scenarios for the first and last year of the benefits period. In this case, we have 10 pedestrians and 5 bicyclists ADT in the first year for both the build and no-build scenarios. In the last year of the build scenario, we have pedestrian ADT of 15 and bicyclist ADT of 10, demonstrating induced demand. So we're going to enter those values now. The ADT values will be automatically calculated for each year of the analysis in Table 55 below. And we provide an explanation that this data is based on trip analysis described in the BCA narrative. In Table 48, we select the improvements the project will make to pedestrian or bicyclist facilities, and we need to be sure to enter the appropriate values if the improvement comes in degrees. So in this example, the project will add 6 feet of sidewalk by introducing a new sidewalk, which will induce additional pedestrian and bicyclist ADT. The project will also install a new marked crosswalk. We enter yes for the extend pedestrian sidewalk width, and we enter 6 in the sidewalk width additional feet. The project also installs a new crosswalk, so we're entering yes, and it asks the average number of crosswalks on the new unmarked crosswalks per trip. We enter 0.5 to say that the half of those trips cross the road at that time. In Table 49, we enter in some additional bicycle and pedestrian information. We enter in the trips induced from non-active modes, and the USDOT BCA guidance recommends a value of 89%. The length of the new or improved pedestrian cycling facility is 1 mile, so it extends beyond the bridge itself. In the next section, we enter other quantified benefits not captured elsewhere. In Table 50, we select yes because the project has other benefits that are not captured elsewhere. In Table 51, we enter that there are reductions in temporary loss of emergency services due to the project. The annual benefit is $50,000 in the first year. It has an annual growth rate of 1%. The first year of benefits is 2028, and the last year of benefits is 2057. And there's a study that's included in our application materials for the explanation. In the next section, you can enter the AADT by mode and year manually, if desired. This would be appropriate if you have travel demand model estimate of AADT that you want to enter for the build and no-build scenarios. For this example, we toggle the drop-down in Table 52 to show that the Table 53 changes its inputs. If you do select yes in Table 52, you need to explain the source of the manually entered data, and then you need to be sure that in Table 53 you provide all the ADT for the passengers, trucks, bus, pedestrians, and cyclists in the no-build and build scenarios. The tool will enter 0 values if you leave the cells in Table 53 either as a dash or leave them blank. If you do select yes in Table 52, in Table 54, the values for AADT for all the modes and scenarios that we've entered in previously are 0. They're zeroed out because the tool is looking for the AADT values in the manual table, which does not have any data supplied by us. Enter values in Table 53 to see those values in Table 54. Selecting yes in Table 53 does not overwrite our earlier AADT values in the previous tables. And when we select no in Table 52 and go back to Table 54, our values for ADT that we've entered in above in the previous tables are now captured here in Table 54 from the calendar year 2028 through 2057 for both the build and no-build scenarios. In the next section, you can review the emissions rates per mile. Table 55 contains the inputs used to select the emissions values. In this example, our detour route is a rural interstate with an average speed of 60 miles per hour. Table 56 contains the calculated emissions rates per mile for each emissions category and for each vehicle type based on the speed and roadway type of the detour. Finally, Table 57 contains all the calculations for each year of the project and for each benefit and cost category. Tables 55, 56, and 57 are for reference and should not be adjusted. It's important to note that the resilience benefits are calculated all together in one column, including the safety and travel time benefits. The total benefits information row can be found on Table 1 of the Results tab. On the Results tab, the results from our new Bridge 2 project is included in Table 1 of the Results tab. And Table 1 contains the same benefit and cost values for every category for the example project and our project. To demonstrate the sensitivity analysis, we will create a new sensitivity analysis for the bridge we just created called New Bridge 2 _SNS by clicking the button to add a sensitivity analysis at the top of the active bridge sheet. To demonstrate how we can use the Sensitivity Analysis tab to change the results, we will adjust the AADT for passenger vehicles in the project close year for the build and no build scenario from 14,245 to 10,000 in Table 3. This will reduce the AADT for passenger vehicles in future years and will reduce the benefits associated with vehicle volume. Now on the Results tab, Table 1, the results for the New Bridge 2 SNS analysis is reduced to 1.35 BCR compared to the original. By walking through this example, we have demonstrated all the functionality of the tool and explained how you can use the tool to calculate benefits and costs for your project to produce a complete BCA. This concludes our training video for the Bridge Investment Program BCA tool. For more information, you can go to the program website at www.fhwa.dot.gov/bridge/BIP. And for contact information, you can email bridgeinvestmentprogram@dot.gov. Thank you.
Learn more at www.fhwa.dot.gov. Follow the Federal Highway Administration on Facebook, Instagram, Flickr, LinkedIn, Twitter, and YouTube. The U.S. government does not endorse products or manufacturers. Trademarks or manufacturers' names appear in this video because they are considered essential to the objective of the video. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any one product or entity. Except for any statutes and regulations cited, the contents of this video do not have the force and effect of law and are not meant to bind the public in any way. This video is intended only to provide information to the public regarding existing requirements under the law or agency's policies.